Why is everyone talking about Apache Iceberg? Because I have been here at this conference 3 years ago trying to get people to stop talking about Iceberg and not care about data formats at all. So in this talk, we'll kind of go through that, see why I want to be the only one caring about this space, and then sort of why I think people actually are still talking about Iceberg for some reason. So let's get to it. This talk doesn't really work unless you know I actually did start the project. So I was the original co-creator of Apache Iceberg when I worked at Netflix. I've since moved on. I founded a company called Tabular, and last year I moved over to Databricks. So yes. All right. What we're going to talk about today, it's basically an overview of the last few years. So what is Iceberg? Why you pretty much should not care or focus on Iceberg, and then really why people do anyway. And then I'll go a little bit into what's coming up in the project, how it's evolving, because you're going to ask anyway, so may as well. So if that sounds fun, let's get to it. So in order to answer this first question, what is Apache Iceberg? I do need to take you back in time a little bit. Back when we weren't so spoiled with databases like Snowflake or Databricks that just worked all the time, back basically to Hadoop. So who remembers data engineering in the era of Hadoop? Okay, I'm seeing some hands. This is great. I love this Easter analogy for the old Hadoop days because there was a ton of enthusiasm, but the tools that we had just were not up to the task of getting eggs across the finish line. We were running so fast, trying so hard, but we really didn't have the tools, and so it turned into pretty much, as you can see, a total mess. And that was when we started looking at this problem when I was at Netflix. So Iceberg's origin is really because we had three big problem areas. The first was correctness issues, which we we just had coming out our ears. In the old days in Hadoop with Hive tables, you couldn't actually go make some arbitrary change to a table. If you needed to add data to the same partition that you were deleting data from, you couldn't do that atomically. You had to choose whether you wanted to duplicate data for some period of time or lose data for some period of time. You couldn't have it both ways, which is kind of a ridiculous correctness issue for something that we treated like a database at the time. Then there was this other aspect of cost and performance. We were trying to go faster and faster, but the representation and metadata that we had about data in our tables was insufficient. It was, hey, I think there are some files that were maybe like from last week, go find them. And that's literally what the database would do. It would go find the partitions for last week and then go ask Hadoop what files were there, if there were any. And we couldn't do things like go look at an individual data file, look at the ranges of values within that data file, and decide whether or not we need to read it. You had to basically go do thousands of file listing operations and then read any data files that turn up, even if they duplicate data and things like that. And then the last area that we were looking at was data engineering productivity. And I know that the cost and performance and correctness issues are also big drags on data engineering productivity. If you can't trust that when your Hive query crashes or your Hive write crashes, that it didn't just corrupt your table entirely, that's a pretty big problem. But there were other more subtle things that we didn't even think of as correctness problems at the time. So what we realized was that all of these challenges were simply because our tables, or the representation of data that we use to think of as a table, were insufficient. They were very simplistic. It was just, hey, let's treat a whole bunch of directories of data files as though they're a table. with no notion of, what is the current schema? How did that schema evolve over time? How do we know that a column is the same or not? And so what we did was just throw a whole bunch of techniques that we learned from real database people at the problem and see what happens. Now, it's simple things like this that we take for granted. So in the productivity area, this was literally the same change when we were working with a Hive table. So if I rename a column from ID to profile ID, or if I drop the ID column and add an entirely different new column called profile ID, are those the same change? Of course not. Rename preserves values. Are these the same change? If I drop a column and then add a column with the exact same name versus just leaving it alone? No, of course not. Drop discards the values in a column and you get an entirely new column after that. So when I say database fundamentals, I really do mean fundamentals. Like, we just need things to work like SQL tables. Because if they don't work like SQL tables, you end up with all sorts of problems. Because the expectations that a data engineer has for how they're interacting with a table and what is going to happen are broken all over the place. And that is unfortunately the state of the world as of, well, really 10 years ago, 7 years ago. I forget when we started the project. So what we wanted to build and what we ended up doing with Apache Iceberg was to create an open standard for tables, and we got as close as we could to SQL behavior by borrowing or stealing a whole bunch of great ideas and designs from the database world. Now, crucially, we screwed this up in one important way that we'll cover. But what we ended up building was exactly that. Essentially, Iceberg is a way of tracking table metadata other than using directories in a file system that upgrades our tables to perform and act as though they were tables in a real data warehouse. In fact, I think now we kind of consider Iceberg tables to be, a fundamental component of data warehouses, but really we were just trying to mimic that behavior at the time. So we needed things to address all of those areas I talked about. We wanted them to make people productive because you could rely on SQL guarantees and SQL behavior. We wanted transactions to either complete entirely or make no changes to a table, never leaving you in this state where you just don't know if you can trust the data anymore because something failed. Data engineers were constantly tracking down bugs or problems, or it was just not uncommon to come in on a Monday and go, I guess I have 1 million duplicate rows. Wonder where that came from. Guess I'll go clean it up. We wanted to have things like schema evolution to get rid of the zombie data problem. Enable things like merge statements and better declarative SQL. And critically, we also wanted this to work with all of the systems that we were supporting on the Netflix data platform. So we had, at the time, Pig, which thankfully is gone, Spark, direct Python access. We were writing to tables through Flink. We had a huge variety of engines, and we had no way for those engines to coordinate with one another. So we needed a safe way for all of those products and open source projects that we used to coordinate and not stomp on one another, not corrupt tables, and not see intermediate states. So that's what we set out to do. Another thing about this is if you have a system in which you are you can't coordinate across those engines that don't share any architecture, then you have to copy data between them. And those sync costs and those copy costs are an enormous tax on data engineering. So we didn't want to have to keep one copy for Flink and then snapshot the table and move it over for Spark. We wanted to share a single copy and do that reliably. We also found some opportunities for new capabilities from just how we were representing data. Because we're using Hadoop, which was I think append-only store, and things like S3, we were using S3 at Netflix, we couldn't go back and use B trees or common data structures for evolving data within data files. So we ended up having a Git-like model where you constantly keep essentially a metadata tree with data files at the leaves, and you evolve that over time. And that gives you some really nice features, like the ability to roll back to other versions or time travel at query time. That also enabled us to build things like branching and tagging. So you can tag an important version and then have it automatically forgotten when it times out and you no longer need it, which is great for situations like financial auditing, where you have to keep it for 2 years, but you don't want to keep it any longer than that. So we set out to build this, and that was basically my talk 3 years ago. What we built and why. But I was also saying that you shouldn't care about Iceberg 3 years ago. So once again, why am I here? And why was I arguing that 3 years ago and no one listened? Well, it does seem like we do need to care, because these are fundamental challenges of what we were working with at the time. And so it was really important to solve the challenges of dropping a column, right? So what I'm saying today is just to clarify a little bit. You might need to care about Iceberg just a little bit, but I think there are 2 ways in which you really need to care. The first is data quality, and that's what I was talking about 3 years ago. Data quality is incredibly important. You should never have a situation like this, where you drop the column and it came back for some reason and it leaked into downstream, and now you got to go clean that up, and someone's got to go talk to the executive staff who read that report and maybe talked about it on an earnings call. Not that that's happened. We just want it to be like this. I dropped the data. What do you mean? It's gone. We don't have to worry about it. And that's that's what I mean when I say people shouldn't care about Iceberg. You should care about the SQL semantics of the tables that you're working with. We should just have the common set of semantics and expectations, and you should never be surprised by what your tables are doing. Now, another way you should care is you should really care about wasting time. And that's why people care about Iceberg today, I think. So I think that this comes down to architecture and sort of the architecture that Iceberg unlocks, which is, I think, why we're all discussing it now. So that brings us to kind of chapter 2 of the talk, which is the happy accident. So why do people actually care about Iceberg? All right. Well, the thing that I didn't realize, and this is the mistake that we made, this is kind of like, when a high school student or college student comes into class late and they're talking about some conjecture and he thinks it's homework and goes home and solves it. That's kind of what happened. Not in a big way, but data warehouse storage had never been reliably shared. We just didn't architect databases with shared storage in mind. We always had a compute layer and a storage layer that were very deeply entwined. That just, that was how you built databases. Why would you do anything else? You put security at the top, then a query layer, then the compute layer, and then you have storage down at the bottom, and everything's all clean. Why would you want to share it? But Iceberg accidentally built reliable shared storage because we were coming from this Hadoop world, where we had Hive and Pig and Spark and all sorts of things sharing these data tables at the same time. Remember? I even had it there. I snuck it in. So shared storage, it turns out, is a foundational change, because this is just not how we've architected data storage or analytic databases in general before we had things like S3 and even I think in the Hadoop era, had we solved all of these challenges, it wouldn't have been the same, because globally shared object storage was not a thing yet. So the combination of both a system for reliably sharing storage with SQL and database semantics, plus the advent of object stores that could actually hold and handle the load of some arbitrary number of systems all trying to read the same table at the same time. Please don't bother me about 503s later. I know that's a problem. We'll just assume that it scales infinitely right now. I know people are going to come up with that. Anyway, it was a foundational change. So both the introduction of object stores and the ability for metadata to actually handle share nothing database systems was pretty big, which is why we care about it right now. People want to take care of all of those problems I was mentioning earlier. We want to look at this as a single store of data that you can use underneath Spark, or underneath a SQL data warehouse, or underneath Flink and other streaming systems, underneath graph databases. And critically, you want one set of governance and access controls. You don't want to have to ever copy data and use it copy data to use it in different places. But this is a really big shift, not least of which because databases are used to having that fine-grained control. It's really hard to talk to a database and say, hey, rather than your perfectly tuned, amazing storage system, you should use this other thing because I want Python to be able to bypass your query layer. That's kind of a hard sell. And I'm actually surprised that we're there, but we are actually seeing this shift and this realignment in the data architecture space. And there are a ton of good benefits from doing it. It means that we won't ever have to, well, shouldn't say ever. It means that we don't have to forklift data from one system to another to use a better tool. It means that we don't have to maintain pipelines that all they do is check whether copy A is in sync with copy B and whether or not we read copy B and, again, put that in a report that someone important read. It is a really big shift to allow us to use the tools and to save time. So what we're seeing is centralized data and specialized compute. And this is really cool. I think that this is, I care about tables, so I think this is great. I think it's pretty fun. But I love this world where you're in control of your data and you provide access to that data to systems that need to use it. So the security and governance is all at the data layer, and you can allow any tool to access it, whether that's a Python process running in EC2 or a full SQL data warehouse that's amazing and has all of your cost-based optimization. Everything should fit together very cleanly. I love to use the Lego analogy, and this has to be built on open standards like Iceberg. So Iceberg tables. We're also expanding into Iceberg views. There are several companies, at least, I know using Iceberg views. We're also trying to standardize new things like the protocol that you use to talk to a catalog. So how do you know what tables exist? How do you interact with those tables? How do you commit? That sort of thing. Now we're trying to standardize that so that you can plug and play different catalogs so that you can not choose a single provider and be locked in anywhere. It also supports declarative patterns and services and all sorts of good stuff. So I think that is, really why we're talking about Iceberg. It's this realignment. Some people would call this like a lakehouse pattern. I think the definitions tend to differ, but this is what I think of when I think of a lakehouse pattern. So that's what Iceberg is, how the project got started, what it is today. I also want to talk a little bit about Iceberg's future. What are we working on now? And how is Iceberg getting better to meet all of those use cases that you guys no doubt have, because we do it all for the data engineers. Well, I would describe the next chapter in Iceberg's evolution with one of my favorite XKCD comics. It's all about standards. And what we ended up with was a situation in which we had competing standards, because I actually think that one of the forces that drove us all to build these systems was the addition of object stores like S3. When S3 came out, all of the problems we were facing in Hadoop got worse. So when we were listing directories in HDFS to plan scans on our tables, it was kind of okay. It wasn't wrong that often. But in S3, when you had no consistent listing, when listing itself took 10 times as long in terms of every listing call to S3, things got really bad. And they were so bad that we actually had to solve this problem. So that's one of the reasons why we did it. And at the same time, my now company Databricks had the exact same problems. They were building cloud-based architecture using S3 as the primary store. So it's not all that surprising that we solved the same problems in kind of the same ways. So where we're heading now, or at least where I am heading with the project, is to try and bring those two things together. So Databricks acquired my company last year, and the purpose really is to bring the formats closer together and get us back to this original vision of a shared and universal standard for data at rest in object stores. So that's where we're kind of heading, and I'll give you a taste of what we've been working on with the community. So V3 is the hopefully coming soon format. It's the next evolution of the Iceberg format. And what we're trying to get into it, in addition to some just new features that are great, are additional features that align and have been built through collaboration with people from the Delta community, and just basically the Iceberg part of bringing the data layer together. So what are those things? Well, first of all, this is the flashiest one because this is awesome. I love the variant data type. It is a collaboration between communities. This was introduced in the Spark community by Databricks. Snowflake picked it up and proposed it for the Iceberg table format. And so this is really a universal data layer concept. But it also is just something that we should have done a long time ago. So I'm actually stoked about this as an addition to the format, because we've basically said for the longest time, you shouldn't be putting JSON in your tables. I don't know, I don't want to know about it, but we all do it. Come on, I've done it. The data model at Tabular for all of our event data coming off of your catalog was JSON hitting Iceberg tables. So you can see that this is a big problem. Anything where you're streaming data, you want to have the ability to rapidly change it. Maybe you're working with deployed code that just produces what it produces, and you don't get to decide, hey, can you go change that to fit my table format a little bit better, or my table schema a little bit better? And what we also need is for this to be super fast and for you to get close to columnar speeds with this data. And that's exactly what the variant data type tries to deliver. So I'm really excited about this. This is a new feature that is going to be supported across a number of different commercial engines, including Databricks, as well as Spark, Delta, Iceberg, Parquet. We're actually doing the standardization in the Parquet community. So this one, I think, is a really big win for the data community. Sort of along those lines, we also have geospatial data types. So this whole realignment, the transition to centralized data and specialized compute, you would think that that would fit really nicely with GIS engines and use cases that have geospatial types. But we simply didn't support geospatial types in the past, so you were kind of out of luck. But what we've done is we've gone together and, also in the Parquet community, we've worked across a number of projects to try and standardize the metadata that you need as a writer to produce, the metadata that readers can consume, and to try and sort of bring down the complexity in this space so it's on the writers and not the readers, so that you should be able to very easily consume geospatial or map data anywhere. And also have all of the fidelity and information that you need to work with it properly downstream. So this was a huge collaboration across a number of different companies, and I'm really excited to see it going in. We're also introducing a couple other things that are just better for the format. So first of all, we're introducing row-level lineage information. So you'll be able to better construct changes that occurred in your tables. So if you run a merge command, for instance, and you merge by some ID, you're saying take these new rows, match them to my existing rows by some ID. Well, we had no insight into which rows correspond in the data before the change and the data after the change. Not only that, if you were using a copy on write strategy, you might have a whole bunch of unchanged rows that just were along for the ride, going from one data file that gets deleted straight into another data file that gets added. So we're solving those problems and bringing you better incremental data for consumption and debugging use cases. Because if you need to know what was wrong with that merge statement, just knowing that these 1,000 rows were replaced with these 1,500 rows does not really help. We're also bringing some of the improvements, I think, from a lot of different ideas in with deletion vectors. This is probably the most technical slide that I think almost no one cares about at a data engineer focused conference. So I'm just going to go and say merges are going to get faster, and we think that this is better overall. The high level idea is that you have to maintain your table, and people just weren't. So we're making it so that you are forced to maintain the data in your table rather than have it so that 1,000 delete files can accumulate for a single data file. We saw that pattern a lot, and we really just should not have been so permissive. All right. The next thing, those are all things that are coming in V3. I'm really excited about those, and I'm really excited about the collaboration that led to those things coming. There's even more than that. There's like default values and all sorts of things. But I want to take a little bit of time to talk about V4 as well. V4 is, again, with our goal as Databricks of bringing the formats closer together, V4 is what we think of as ideas that will make that possible. Now, of course, this is future. So I have a brief disclaimer, which is that these are my opinions. This is just some things that might happen, but we will work with the community to figure out and design all of these things. And we don't make decisions in the Iceberg community. These are my opinions. So, yeah, exactly. Shut up and get to the point. All right. So I would describe V4 as basically Iceberg metadata has aged. We created the project in 2017, which makes it almost 8 years old. So we've found things over the years that can or should be improved. And that's what I want to work on in V4. So first of all, one thing that Delta is very good at is small writes. In order to write to a Delta table, you only need to write a single metadata file. That's really nice. In addition, on the read path, Iceberg needs to read multiple data files. It needs to read a manifest list. Sometimes you even still go and read a metadata file. We can do better on those for small tables. We also want to avoid metadata compaction and basically needing to do more work with metadata than necessary. So how do we avoid rewriting files? How do we avoid writing small files and needing to compact them later? We also have some technical debt from just things that we did in the past that no longer makes much sense. So now data infrastructure is moving away from partitioning, finally, because partitioning is a really rigid structure where you say, my data is always going to be in day-sized chunks. Well, what if you need to move to hour? That was one thing that Iceberg did well. It said, okay, well, we can change how big of chunks we store your data in. But even then, what if it is, you have skew in the hours? Say you're a, video streaming service, and most people watch TV at night when they get home in the evenings. That skew is a problem for all partition tables. And if we can cluster data effectively, we don't really need to be so rigid. But metadata assumed that partitioning was a thing. And so we don't have metadata filtering. This also doesn't work all that well with geospatial data that doesn't partition well. We also have a situation in which you have to rewrite metadata for disaster recovery. You can't copy files from one place put them in another bucket, and have everything just work, you actually have to rewrite metadata because we require fully qualified paths. So there's just some problems where Iceberg has aged. And what we want to do is solve these problems. We want to get to a place where we have single file commits. So this is faster commits, lower latency, without sacrificing the read path. So you still have single file metadata reads as well for small tables. So single file commits, single file reads. To do that, we want the metadata tree used by Iceberg to be adaptive. So you don't have a rigid structure of metadata, manifest list, manifest data files. We'll collapse some of those areas if you don't need them for the size of your table. We also want to use logical deletes, much like our deletion vector work, so that you can avoid rewriting metadata files all the time. We're going to revisit some of those old decisions, introduce relative paths, columnar metadata, and column stats for metadata skipping. So I'm really excited about the evolution that we're going to be undertaking in V4, which is, I think, the next thing right after we close out V3, hopefully this month. So with that, that's about the end of my talk. I just wanted to bring it back to where we started, which is, why are people talking about Iceberg? And I think it's because Iceberg's original goal was really to be this ubiquitous table format. We wanted it to be something that everything supported. We wanted it to be built into, we dreamed of Redshift and Snowflake, and that's happening. That's pretty amazing. It unlocks this centralized data architecture that just saves a whole lot of time for everyone out there. We love data engineers, and I hope it makes your lives a whole lot easier. And I'm really excited about all of the changes that we're making to make it even more ubiquitous, to make it more like Delta, to collaborate with the Delta community and really move this area forward and make something great that lasts a long time. So thank you all for listening to me. I appreciate you showing up.